Okay, I'm going to continue and talk about the second part of the homonuclear to the fluorine-fluorine spin exchange experiment, and then I move on to the heteronuclear situation of how to measure distances. So I talked about the isotropic shift different exchange. So traditional, what you think about into the correlation experiments measured cross-peaks. But you could also have the situation where you have the same isotropic shift, but of course, between neighboring molecules, the orientation won't usually be the same. And so you have a distinct anisotropic chemical shift. And that can be taken advantage of by the technique of CODEX, which is a principal technique I want to emphasize. Anisotropic spin exchange by CODEX was really first developed by Klaus Schmidt-Rohr and co-workers in this paper. The first author is Eduardo de Azevedo. It's a very clever idea developed to look at slow exchange or motion on the tens to hundreds of millisecond time scale in solid state NMR under magic angle spinning. And in my group, I simply tailored that experiment for the purpose of not studying slow motion, but to study spin diffusion and counting the number of spins in an oligomeric complex. And let me just show you the pulse sequence. The pulse sequence can study either. And the idea is you want to have a train of 180-degree pulses that come out every half rotor period. So I'm having these magenta pulses. They're all 180-degree pulses. They're synchronized with rotation. And the rotor period is indicated at the bottom here. Every rotor period contains 2 pi pulses, spaced by half a rotor period apart. One pulse occurs in the middle of the rotor period, and a second pulse occurs on the rotor echo. And the purpose of this pulse train is to recouple the chemical shift anisotropy. Proton, meanwhile, is decoupled at the dipolar decoupling here. So for the X being the only orientation-dependent interaction, the only anisotropy is the CSA. So these pi pulses will bring back the CSA, prevent the refocusing of the CSA by magic angle spinning. So that's all good. You have the CSA recoupling here. And then what happens next is you have a 90-degree pulse happening on the rotor echo. And this stores the magnetization along the Z direction. And then you wait a mixing time. And sometime later, you put magnetization back to the transverse plane. And then you do the same pi pulse train, again, CSA refocusing. And so the idea of the second pi pulse train is to basically unwind the effects of the first pi pulse train to recouple the CSA. If during this mixing time, nothing happens, meaning the molecule is not doing a slow reorientation, or the magnetization of one spin is not having a neighbor, another spin that's close enough, then the magnetization during this time won't change. And the purpose of the second pi pulse train is to cancel the effect of the CSA recoupling of the first one. And the detail of that cancellation, the 90-degree pulse phase has to be controlled just right in order to actually for this cancellation to occur. And then after the second pi pulse train, you have another Z filter, a pair of 90-degree pulses, TZ, is usually a much shorter mixing time. And the reason for having a second mixing period, longitudinal waiting period, is for controlling the T1 relaxation. Because as you wait 700 milliseconds or something like that to observe something, whether that's slow exchange rotation or spin diffusion, your T1 relaxation is happening. So even when there is no motion or spin diffusion, you could have intensity just dropping because of T1 relaxation. That's not of interest. So having a second TZ period is to allow you to run a control experiment where you switch the magnitude of TZ and TM. You can make the first period really short, TZ, and make the second period, TM, longer. So that becomes your control, because you can imagine when you make this first period short, then you don't give it enough time for the magnetization to do anything. And so the 2 pi pulse train CSA recoupling will cancel. So you'll get an echo back. So the idea is if nothing happens here because the time is short or because the molecule is not doing anything interesting, then by the end of this second pair of 90-degree pulses, you get a whole echo. And that is called a stimulated echo. And so if that's the case, well, nothing interesting is happening. But if you do the real dephasing experiment where this Tm is long, Tz is short, and the molecule is either rotating, slowly reorienting, or one fluorine is close to a few other fluorines, the magnetization will transfer. And you know, if the magnetization is transferring, then because the tensor orientation is different, your CSA will be different. And if that CSA is different, in the second half, then the recoupling won't be the same frequency as the first part. So that means your echo intensity will drop. So this is the idea that I try to sketch for spin diffusion in this case, where your one tensor, fluorine tensor, or carbon tensor, for that matter, any tensor, can transfer magnetization to the next tensor that's oriented a little differently. And then after the mixing time, the recoupling will occur in a way that makes your echo intensity drop. And so you follow how much that echo intensity will drop every time you would divide by the control experiment as 0 intensity so that you factor out the T1 relaxation. And that will tell you, in the case of spin diffusion, just how many neighbors you have for the central spin. The idea is that if, say, you have a cluster of 3 spins with the same isotropic shift, but different anisotropic shift, then as your magnetization gets spread and equilibrate among all 3, then the original site will only retain 1/3 of the intensity that is at the same tensor orientation as before. This slide doesn't have a typical picture. So if you have 3 spins and you started out having intensity all on this, by the time you equilibrate your intensities, each one will get 1/3, assuming these spins are not too far from the original one. So and the CSA, the stimulated echo, detects only the amount of the magnetization which stays in the original tensor orientation. Right, so that's the idea. So you have, the point is these tensors are differently oriented. This is maybe my Z, this is Y, this is X. So whatever magnetization gets pumped to these orientationally different spins, they don't get detected. My echo only detects the original magnetization. So that's the idea. And that's what we would like to use it for, because various examples where you would really like to know what is the number of spins in that cluster. You want to do spin count. The nice thing is that the trajectory, the rate of intensity decay as you reach that equilibrium, that depends on the distance among these spins. So the equilibrium echo intensity, first of all, that echo intensity at equilibrium is 1/n, where n is the number of spins in your local cluster. And then the rate of that decay follows this equation. Your magnetization at time t later going to be related to the initial magnetization through this exponential matrix, where this K, the rate matrix or exchange matrix, has these components for the case of a 3-spin cluster. And you have these rate constants, and these rate constants are kind of analogous to the concept I talked about earlier for isotropic spin exchange, where again, these small k ij's between spin I and spin j, or ABC, whatever you call it, is going to depend on the dipolar coupling squared, which means that it'll scale with 1/r to the 6th power. And then it's going to depend on the F0, this overlap integral, and that's again going to depend on basically how different the chemical shifts are, in this case with CSA, and then basically the chemical shift properties. So this is the idea of CODEX, and I want to show you an example of how the data would look like as applied to fluorine. Here, imagine you really just have one chemically unique fluorine spin, one per molecule, all right? And it has a certain tensor property. And you have an oligomer complex. And in this case, it's a membrane peptide made of the SARS envelope protein, transmembrane domain. And we just tagged each membrane peptide with a single fluorine. And in this case, it's at the parafluoral position of the phenylalanine residue in this peptide. In this case, we handled it by chemical synthesis of the peptide. So if you look at the fluorine spectrum, it's a very simple spectrum. It's literally one peak, right? And I can measure that in the S0 experiment, where again, this first mixing time is short, the second one is long. And I forget to say, between the control and the dephase, the sum of the two, Tm plus Tz, is the same. That's why I say you can factor out the T1 relaxation. And then I flip, the TM is the long one first and then the short one next. That's my dephasing. And you see that I can take examples where I went out, I think maybe 3 seconds. Basically, when you wait it long enough, the TM, you can see how the dephase experiment shown in red is so much lower than the control one. And how much lower, you look at the intensity, in this case it's 0.2, and with a certain error bar, so you see that, okay, I have, in the end, when everything is equilibrated, I have a 1/5. In other words, I have a pentamer for this membrane peptide. And I care to know this because in the literature, people debating whether this peptide makes a pentameric channel or who knows, tetramer or hexamer. So that's the kind of questions I can answer. So I can also then fit the decay trajectory using that rate exchange matrix approach to get distances. On the right is just another way of showing the same data. You see this decaying way of showing it is S/S0 as you increase the mixing time. But if I just flip way I divide the intensity, S0/S, I can show a little bit more clearly that indeed the intensity equilibrates at 5. So if you ever wonder, well, can I tell a pentamer apart from a hexamer, then you can start to look at the inverse way, whether it equilibrates to 6 or 5. Potentially a little harder to tell. So in this case, we know, and we were also changing how much protein I put into the membrane, whether it's diluted enough or whether it's a bit concentrated. As you can imagine, as I start to have more and more oligomer assemblies in the membrane, then you might start to see couplings or spin diffusion to the next oligomer. So that could get a little harder to tell. All right, so this is somewhat of a busy slide to make 2 points. One is when you do these CODEX experiments, you say I'm spinning at maybe between 10 to 25 kilohertz, or maybe I want to go a little faster. I can still run these experiments with these high pulse trains, generally without too much problem. You don't want to go too fast. But then during these waiting times, should one do nothing on the proton side? Or should one do a little bit of irradiation in a DAR-like fashion to recouple the proton to the fluorine? Basically, you can see here, that's what we're doing. We're fixing the spinning speed at 25 kilohertz. And the first decay comes down relatively fast. And this is when we're not irradiating on a proton. We're just leaving it alone. And then when you get to here, we're irradiating on a proton, and it actually becomes a very slow decay. And if the CODEX decay curve doesn't drop to equilibrium fast enough, then I won't be able to see the final value. That's detrimental, not good. And so you might ask, why is it dropping slow? Now, previously I said, when you do normal 2D exchange, turning on the proton to match the spinning speed is a good thing because it makes spin diffusion more efficient. And here it does the opposite. This is a very slow decay. So we don't want that. We want a simple experiment where you don't do any decoupling. The reason for that, why CODEX behaves opposite to the isotropic spin exchange, is because you're having the same isotropic shift here. You're no longer having 2 different isotropic shifts. So if you are not doing any proton irradiation at all, you would have a pattern that's broad. So you can actually cover the CSA anisotropic spin exchange. If you're starting to irradiate, you're basically making the single peak sharper. And so it's not going to be as good or as effective in doing the anisotropic spin exchange. So it's because in CODEX, there's only a single isotropic shift that makes it actually better to keep the things, the zero quantum line shape a little broader, and don't do any proton irradiation. So follow the simple approach. I think the second MAS dependence does not really make too much more new points here. Let's just say if I stare at this panel spinning at 25 kilohertz, and what I'm plotting here is the KSD, the spin diffusion rate, as a function of the proton decoupling or proton irradiation. And here, what you want is as high as possible, because that means my buildup rate is efficient. And when is it low, you get these dips when your proton irradiation is coming out at either equal to omega r or 2 times omega r. So you're having resonance condition, you're now recoupling. So this is the same thing as saying, don't do any recoupling when you're doing CODEX, because recoupling actually makes it worse. And so actually, this is the DAR. You don't want that. You want PDS. I just said it here. This is the one that is efficient. So, all right. So now let me go to something a little bit more on the practical side. In my lab, we have basically two HFX kind of systems. And this is the Booker design, what equipment you need to do any of these fluorine detection with proton simultaneous pulses. We need two sets of filters that come from the proton and the fluorine channel on the console. So you need to have two high power amps that are both close to the proton or exactly at or near the proton frequency. So on a 600 megahertz machine, you kind of need two high power amps that can function at 600 megahertz or 564 megahertz. And then you go through these filters. The proton channel will block out the fluorine, and fluorine channel will block protons. And then you combine them into one line, and that line, and then it goes into the probe. And on the probe side, these actually share the same input. And the isolation between the proton and fluorine channel is achieved by connecting the tuning components. This is the fluorine capacitor, the fluorine tuning side. This is the proton side. And they're connected by a quarter wave transmission line. This is the Booker HFX probe design that gives you an idea of the input side fluorine and proton. So you have two independent tuning for the two channels, and then you have a combined matching capacitor for the two channels. So that's a relatively separated HFX, nice, separate, taking care of the two needs. But we also have a 1.3 millimeter probe that is HCN, but the H side is written as H dash, which means that you can actually tune the proton channel to the fluorine. And this is, if you can sort of forego proton decoupling, then you can just say, okay, I'm going to do fluorine, carbon, nitrogen. I just don't have proton. And various people have done that. And you basically play with this quarter wave cable, adjust this position to switch it from the proton frequency to the fluorine frequency, just a slightly different position along this line. So that is doable. And since probe is a 1.3 millimeter, you can spin fast enough that you can actually get away not worrying about proton decoupling. But then second part of this talk, you have to have HFX because you really need to have simultaneous pulses coming out. You cannot forego the proton channel. So I want to come back and lean on the HFX probe. Now I want to talk about heteronuclear experiments, distance measurements where fluorine is present. The main experiment that I would say in solid state NMR everybody benefits from is the Jake Schaefer experiment and Terry Gouillon's original development around 1990. It's a REDOR experiment, rotational echo, double resonance. The basic idea is sketched out here. This is from Krystianiak's notes from winter school. The most common implementation is for carbon-nitrogen distance measurements. The idea is to put a pi pulse on the observed channel. Normally, we like to look at carbon. And then you put a bunch of pi pulses on the nitrogen channel. And again, the pulses come out every half rotor period. And you do this half, whole, echo, half, echo. Then you have one pi pulse by the carbon channel. Between the two channels, in the end, when all is said and done, you need to have the situation of two pi pulses per rotor period. But the observed channel gets one. And so the unobserved channel skips that. And then you go on and you need to have equal period before and after the single carbon pi pulse. So the idea of this combined set of pi pulses is first, you want to refocus the carbon chemical shift evolution. All right, you want that to be refocused. And then you want to recouple the carbon nitrogen or X and Y dipolar coupling. So that's the purpose. By the end of this process, then you have detection on the carbon channel. No other interaction remains. So this REDOR experiment is also done in a controlled way. You have to do two experiments. One experiment actually just have the carbon pi pulse and nothing happening on the background channel. That's called S0. And then the other experiment, you have the background channel, all the pulses come. And the reason to do that is, again, while you sort of wait to have the longer and longer REDOR pulse train in order to measure weaker and weaker dipole coupling, longer distance, you suffer from T2 relaxation, transverse relaxation on the carbon channel. So if you don't have the control experiment where you don't have the nitrogen pulses on, you will see the intensity will just drop just because of T2. You will not be able to figure out what's due to the dipolar coupling and what's due to the T2 relaxation. So you need that control experiment. So that's the idea of REDOR. And what is really nice about the REDOR experiment is when you have done the control and you monitor the S over S0, the dividing out the intensity, and then you measure this S over S0 intensity ratio as a function of the REDOR pulse train time, you find this characteristic dipolar oscillation. And this oscillation is universal in the following sense. If you plot the dephasing as a function of unitless parameter, which is not quite time, but time times the coupling strength, then the pattern is always like that. It's the same shape no matter what. It's just going to be this shape. The y-axis is S over 0. The x-axis is not quite time. I want to take the time multiplied by the coupling strength of interest. So, and when you plot it in this way, time times frequency is unitless, then I can tell you at this point, the first zero crossing is a defined value of 1.73. In that sense, is universal. Now, how is this useful? I say, well, I really care to get dipolar coupling. This omega D is what I really want to measure. And as an experimentalist, all I can control is how long I do the REDOR. That's this time. So you realize if you need 10 milliseconds to get to this, then immediately you can say, well, so example, 10 milliseconds to get to a minimum point, then my coupling strength must be 1.73 over 10 milliseconds, and this is 173 hertz. That's my dipolar coupling, right? If I take only 1 millisecond to decay to almost zero, then you know the dipolar coupling is 1.73 over 1 millisecond. Then this is a 1.73 kilohertz interaction. It's 10 times bigger, right? So when you do experiments, you measure this point-wise as a function of time. But you can see here as an example, the first minimum occurs almost at 2 milliseconds. So you can take that and 1.73 divided by 2, you get a hertz. And so this gives you a readout in a very simple way. So we like REDOR a lot for this universal feature. And of course, if your pulses are not so perfect, you have imperfections, then this can be anticipated from numerical simulation, can be experimentally calibrated, not a big deal. All right, so the REDOR experiment is the basis of recent development of fluorine, including REDOR in a two-dimensional way. So again, I sketched the basic REDOR, and I want to show this now for carbon-fluorine combination. But we say, well, in 1D carbon detection, I can only resolve a limited number of signals, so I cannot measure many distances. I sure want to do this faster by doing a 2D carbon-carbon correlation. So I have this T1, T2, this normal 2D kind of carbon correlation template. But then before I start that, I insert a REDOR module where I have carbon here, pi pulse, and then I have fluorine. So it's a simple extension of the REDOR concept to multidimensional capability. Again, I need always a control because the T2 relaxation will always happen. So my control would be the case where the fluorine pulses are simply not put out. Then I can also go to a different way of doing REDOR. Here I want to combine proton and fluorine. If you remember, this is one of the longest distance ruler that I can get to with NMR. And if I want to do that, what would be the 2D I can situate my proton fluorine in? And the best 2D template would be proton detection, direct detection, and nitrogen in the evolution. And so that's my typical solid state version of nitrogen proton HSQC. And I can have CP to nitrogen evolve, and then CP back from nitrogen to proton. And once the magnetization is on the proton side, then I can start to do fluorine REDOR pulses. And then when I'm done, then I do proton detection. So it's a high sensitivity proton detected version of HF REDOR. It's very nice. And I can have another version. This is a 2D carbon-carbon resolved proton fluorine REDOR. The idea here is that I'm not spinning too fast, and I still have the proton pi pulse, a bunch of fluorine pulses, But before and after the proton pi pulse, I have the red zone of FSLG. That stands for frequency switch Lee-Goldberg. This is to take care of homonuclear proton-proton decoupling. And the reason I need to worry about this is here I'm not spinning too fast because I'm generally in the context of doing carbon-carbon correlation. So maybe I'm at 20 kilohertz. So if I'm not spinning fast, then I need to worry about how to remove the proton homonuclear. So that's a summary of the techniques, but here I go into a little bit more detail. Again, the ruler map, and I want to first show carbon fluorine REDOR, the same sequence that I just showed. And here there are some details. So if you caught the REDOR universal curve idea, here you see that things are not so perfect. The intensities don't decay very far down, all the way to zero. The reason for that is fluorine CSA is giving some trouble. You know, if you have large CSA and you're not spinning too fast, then you're deviating from the perfect REDOR situation. The remedy is to simply spin up as fast as the fluorine CSA would be. So that's this diagram. So here I'm showing that if you spin at 50 kilohertz, then even if you have a very large CSA, my REDOR dephasing will pretty good. So these numerical simulations predict very well what you would find. All right, so how do these experiments look when you measure the spectrum? So because we're doing REDOR, we have to control for T2 relaxation. It's just now I'm controlling it in 2D fashion. You control S0 experiment, 2D carbon-carbon correlation, and this is on GB1. I've already added a REDOR mixing of about a millisecond. And then I did another experiment with S. I have the fluorine pulses on. I'm not showing you that S spectrum because if you just look at it by eye, it looks not that easy to tell the difference from the control. What you really have to do is to subtract the two, and that's what we do in REDOR. You subtract the two spectrum, they get the same exact mixing time, T2 is the same, and once you subtract, you start to see that difference. Those are the carbon-13 sites that are near the fluorine, they feel the dipolar couplings, and they show up. Okay, so that's the power of REDOR. And in a 1D fashion, it's the same thing. You would do a S0 and S, you subtract, and you see how much intensity. It's a different spectrum. So this works, and then you can go on to quantify the intensity dephasing pulled out from these 2D resolved maps, and say, all right, if I have a short distance, my dephasing will be relatively fast. If I have a long distance, dephasing is slow. So this is really the quantitative basis for distance measurement by this heteronuclear recoupling method. How well does it work? This slide shows you, even though that we have a pretty complicated situation where I have one model sample with 3 fluorines, and my carbon-13 label spins are coupled to one of these 3, or maybe 2 of these 3, depending on where your carbons are. And so the distance extraction would not be ideal, but even with that non-ideality, you can see that my y-axis, which is the gold standard PDV-based distance from any particular carbon to the nearest fluorine versus my measured distance, which comes out of these REDOR fitting, the agreement is not bad. And the slope of the solid line is 1.1. So it's not exactly 1. 1 is what you like when things match well. The fact that the slope is slightly deviating from 1 tells you it's in the direction of 1.1. So that means that my measured distances look a little bit shorter than what the true distances should be. And why would it be a little bit shorter? I think this has to do with the fact that if my carbon, one carbon or some of the carbon sites will naturally be sitting in between a couple of fluorines, so they will be seeing the impact of more than one fluorine spin. So the dipolar couplings will look stronger than the distance for it. And so that's probably why you have a slope that's a little bit higher than 1. We also have a single fluorinated GB1 where contribution should be more accurate. In getting this correlation map, we already have taken into account whatever residual motion that these fluorinated side chains would have. And this is something that you have to think about a little bit. Usually these aromatic rings will be moving just a little bit and not much. And how much is much? You can measure the CSA sidebands of the fluorinated tyrosine or fluorinated tryptophan, and you can easily fit these sidebands to get the anisotropy parameter delta CSA. And then you can compare with what is known about the small molecule amino acid CSA. And you can say, all right, the order parameter is slightly less than 1. Your ring is just rotating a little bit. And so then you can take the measured couplings and correct for that motion. If you have an order parameter of 0.9, sort of a little bit of small amplitude fluctuation, then you can say, well, if my simulation is telling me it should be a 100 hertz coupling, then the true coupling should be a little bit larger if your ring hadn't been moving, right, reorienting slightly. So you can correct for that. So that's what we already did in the previous analysis. Okay, the same concept can be carried over to this experiment. This experiment works even better. And because of the proton detection sensitivity, everything is better. So it's a proton nitrogen 2D correlation, but with a REDOR module inserted here when the magnetization is on the proton side and you have the fluorine pulses on. And this experiment works very well because proton is used in two ways. It enhances the detection sensitivity and it allows you to measure a strong dipolar coupling because of this high gamma of both proton and fluorine. In our hands, when we try this on GB1, now it's deuterated and we're doing the proton nitrogen correlation, very nice resolution for this microcrystalline protein. And then you turn on the REDOR pulses and you subtract, again, getting the delta S, the difference spectrum. If you do a short mixing time, only the nearest amide protons to that fluorine can show up in a difference spectrum. If you wait longer with the mixing, then more remote amide protons that are coupled to the fluorine can also show up. And so that's what we are doing here. The delta S map changes with the mixing time, as you would expect. So that's all good. And then I can switch to the quantitative analysis, where I'm looking at S over S0. So instead of the difference, I'm looking at the decay. And remember the universal curve. The decay, ideally, if you have a coupling which is relatively strong, then you don't have to wait very long before you see this intensity dropping to nearly zero. And just based on where the drop happens, you can already easily back of the envelope patch what's the coupling strength. Okay, we get different sites that we monitor intensity, and then we get different distances. And this gives you an idea just from the single incorporated fluorine at a tryptophan 43, you basically can catch distances to various amide hydrogens in a GB1 backbone. So we showed in this paper that you can use this to do the normal structure calculation. You have to assign the chemical ship. You already know that anyways. And then I can say, all right, where are these amide hydrogens relative to that one fluorine thing? So this works very well. You do this at about 40 or 50 kilohertz. Actually, with a 1.9 millimeter rotor, 45 kilohertz is about as high as it can go. And so that's enough for you to get a relatively well-resolved spectrum. It takes about 2 or 3 hours to get each 2D spectrum. And so you see if you have a REDOR curve as mapped by about 6 or 7 data points, then you get 14 experiments because each data point requires S0 and S, right? So even with 12 or 14 experiments, with 3 hours, you can finish it in 3 days, right? So it's a pretty good and very high sensitivity and precise experiment. How well do we compare with the true distance? So x-axis, again, is measured based on the REDOR fitting, and y-axis is the PDB, true distances. Here, I really have a slope 1. I'm not changing the slope. The data points fall slightly below the slope 1. And what that means is that the measured distances are just a little bit longer than the true distances. And that's because of residual dynamics that I haven't factored in. So there's a little bit of motion wiggling of the protein. This is, again, looking at precision as well as accuracy. Now, there's a couple of points that went above the slope 1 diagonal. When it's above, what it means is that the true distance is longer than the measured distance. The measured distance is shorter. And that means the dipolar coupling is particularly strong compared to what it should be. And why is that? These two sites, if you look at it, happen to be at the edge of GB1. So it's not only seeing the same molecules, tryptophan, it's also seeing the next molecule. So there's a coupling is a little too strong. So all of these can be taken care of if you have a real system where the molecules are well separated, protein is large. I will skip some of these dephasing analysis, you got the idea that, okay, CSA tensor orientations don't matter all that much if you're spinning fast. Basically, the CSA gets averaged out more quickly if you're going fast. Any questions at this point? This tensor orientation business, it's less of an impact compared to other experimental imperfections. And the biggest imperfection is RF field implementation. You just cannot be perfect. We run these REDOR simulations using Simpson or spin evolution. Simpson works well enough as long as you don't have too many spin pairs. Yeah, here. Okay, that has to do with frequency switch Goldberg sequence. For this homonuclear decoupling sequence, what is frequency switch Goldberg? You are applying off resonance proton irradiation, and it's very far off resonance. Its off resonance factor compared to the applied field establishes the magic angle. So purposefully off resonance, and I'm also controlling my omega 1. So let's say I want to put out 70 kilohertz omega 1, right? Then I have to be very purposeful that 70 kilohertz on the proton side is not on resonance at all. This is square root of 3, square root of 2, this is 1, that's my magic angle. So then this thing has to be, 1 over square root of 2 times whatever you're doing here, right? So this is 1.4, and so this thing is 0.7 times this. So I'm 49 kilohertz roughly off. And when you do that, if you want your homonuclear decoupling to work, your magnetization has to be 90 degrees from that effective. So it gets very complicated. How do I do that? After I do my normal 90-degree excitation, put things in the transverse plane, I have to give it another 55-degree pulse to put it in the right place in order to have this 90-degree thing. So when we do frequency switch Goldberg, the effective field is very important to think about. And so suppose this is x-axis, this is y-axis. The basic module of frequency switch Goldberg is plus minus, let's say plus y minus y. This is 360-degree rotation, 360-degree rotation, but all in the tilted effective field sense. Okay, and that's your basic element of FSLG. And in order for this to average out the proton-proton dipole coupling, I need to have in this case, the proton chemical shift is also refocused. So it maybe doesn't matter very much, but my magnetization evolves under the FSLG effective field. I still have a chemical shift mutation around the effective field. Imagine you want to do proton carbon correlation in a somewhat old-fashioned way, where you don't want to have the proton-proton coupling around, then you really need to make sure the magnetization is in the right place, perpendicular to the tilted field. And so that's the purpose for the 55-degree pulse. So that's the FSLG train. Is this? It comes out many, just keeps going. The 180-degree pulse direction also has to be chosen right in the context of FSLG. If my FSLG is the y direction, this is not drawn very well, so this should be narrower. This is basically 60, well, 360. You have to work out the right phases for this. If this is plus y minus y, then this is going to be, I think, x pulse in order to have it. I think it needs to be perpendicular to the effective field direction. If the effective field is in the YZ. So it has to be carefully controlled for the phase of the pulse to work. Between REDOR and CODEX, there's some similarity. CODEX, I also have to do 2 experiments. I have to control for T1 relaxation. For REDOR, everything happens when a magnetization is in the transverse direction. So there will be T2 relaxation, and I need to control for that, and that I do this dividing. So how do we use these heteronuclear recoupling techniques? I want to give 3 examples to give you a sense. 2 membrane proteins, SARS, amyloprotein, and then multi-drug resistance, EMRE, and then a third is an amyloid peptide A-beta fibro, where we have a fluorine-bearing PET tracer. In the case of SARS-E protein, what we did was to put fluorinated amino acids into this transmembrane. First, we did the regular NMR carbon nitrogen. We get chemical shifts, we get assignment, all good. And then the question gets hard, because you know that this is an alpha helical bundle. You have 5 copies of these. We verify that this is indeed a pentamer. And then the whole question is, well, how do you know how these pentamers are structured? You know, what are the distance separation between these helices and which residues face the pore versus lipids and all of that. And so here, what we do is to mix in a 1-to-1, 50-50 way, C13 label protein, which we can generate recombinantly, and then we add a fluorinated copy of the protein. You can do this with multiple fluorines in there if you don't care. Just say, all right, all my phenylalanine, I have 3 phenylalanines in this peptide. I'll just bring all of them in. Then the experiment I do is a carbon fluorine intermolecular dipolar coupling, because I'm having 1-to-1 mixture. I never see couplings within the same molecule. It's always interhelical. We do 2D version of carbon fluorine REDOR, carbon-carbon correlation. I can assign reasonably, and I turn on the fluorine pulses, turn off S0 minus S, I do a difference. I see the spectral pattern of those carbons that are close enough to the fluorine. All right, and so those fluorines are the neighboring helix, and in this case, you have these phenylalanines 20, 23, 26. They're actually kind of close to each other, so it's not optimal. So it is kind of a little bit hard to tease out. It became part of the computational pipeline. But anyways, the idea is to use fluorine REDOR in this intermolecular distance fashion. In this oligomeric helical bundle case, we can measure intermolecular carbon fluorine things using REDOR. And of course, we also do various other complementary experiments, not just leaning on REDOR. We also do water or lipid transferred NMR experiments to figure out which residues are facing the water pore and which residues face lipids. And the idea here is to carry out this kind of selection experiment where after proton excitation, you would do a selective 180-degree pulse and basically wait a period. This is a spin echo period. And by putting this pulse on resonance with water, proton chemical shift at about 4.8 ppm, then you basically select the water magnetization, and then you transfer that to the protein in this mixing time. Then you do cross-polarization CP to whichever nucleus you want, nitrogen or carbon, and then you go on and do your regular kind of nitrogen-carbon correlation. So that would be an experiment where you look at the water-transferred residues, nitrogen-carbon plus peaks. You can also change this 180-degree pulse carrier to lipid proton at about 1.3 ppm. Then you will be selecting the lipid proton magnetization, get it over to the protein side, and detect it. So that would be a lipid accessible residue. So I show here the water transferred to the NC correlation experiment. High intensity is shown in blue, wet, and low intensity is shown in red, dry. And since we already know the chemical shifts, I know exactly which residues are dry, which residues are wet. And when we switch to the lipid transfer experiment, we just did the 1D version, not 2D. And you can see, for example, that the aromatic region of the carbon spectrum has relatively high lipid transfer intensities, indicating that these aromatic residues, these phenylalanines 20, 23, 26, overall on the lipid side. These kind of experiments are quite helpful to determine the topology in combination with more quantitative carbon fluorine distances. Okay, so we solved the SARS-E structure with carbon fluorine REDOR as one important element of the quaternary structure constraint. Without that, this kind of oligomeric helical bundles would be fairly hard to get the full structure de novo. The second example is EMRE. This is a bacterial transporter And its function is quite interesting. This transporter pumps out polyaromatic cationic drugs from inside the bacterial cell to the outside. And it does so in gram-negative bacteria, such as E. coli, where this membrane protein will sit in the inner membrane. Takes these drugs from the cytoplasm to the periplasm. So E. coli or gram-negative bacteria have two layers. There's the inner lipid membrane, and then there's the cell wall. So this export goes against the drug concentration gradient, because the idea is, while you try to apply antibiotics, this EMRE defeats that antibiotic action by exporting the drugs against the concentration. The EMRE does so by coupling the drug export with the proton import. So this has been sketched. It's one of the possible mechanistic diagrams that one can think about in terms of how proton import is coupled to the drug export. So what we're interested here is to see if we can contribute to the structure determination of this really complicated protein. And I showed you A and B. What are these? And the two copies of the protein are positioned in the membrane in the opposite direction. So this is an anti-parallel dimer. So it's relatively unusual to have this kind of dual topology. Moreover, this outward-facing, inward-facing alternating axis happens in a way that switches the conformer from A to B for each molecule and from B to A. So this is quite remarkable. Having two distinct conformations mean that in the NMR spectrum, you see two sets of chemical shifts for every residue. And then as you do alternating axis, each set is going back and forth between A and B. This has been already demonstrated by a ZZ exchange experiment in solution state by Katie Hansen-Waldman's group, so they know that this is happening, and so we're not inventing that. That's just the landscape of EMRE, and the question becomes, can we get high-resolution structure of this dimeric, pretty large membrane protein in complex group? That actually, despite a lot of biophysical work on this system for many years, people didn't know the structure to high resolution. Low resolution information is available. There was a crystal structure of the backbone, 3.8 angstrom, and that was good enough to say, definitely you have two copies of the protein and it's anti-parallel, A and B. That part was clear. And then where the drug sits, they know a little bit, but then, even as recent as about 2018, MD simulations have been done in Martin Karpler's lab, and there's another MD group that were trying to build upon this crystal structure information, the backbone, and then use MD simulation to say something about where the substrates would bind, right? So this is actively studied. And so what we did in collaboration with Katie Hansen-Waldman's lab is to basically take advantage of a fluorinated version of a commonly used EMRE substrate, this molecule called tetraphenyl phosphonium. There are 4 phenylene rings, each one actually at a para position. Now, instead of hydrogen, you get a fluorine, and the central atom is the phosphorus. And so that's very interesting. Katie Hansen-Waldman's lab is able to show that, okay, this fluorinated substrate works basically as good as the regular hydrogenated version, and the protein can take that and pump it out. So then we can take this fluorinated drug and measure distances to the protein, amide protons, and figure out where the drug sits. Here's a fluorine NMR spectrum of the drug. All of this is done in the lipid membrane, DMPC. You can see as a function of temperature, at low temperature, what's the rigid limit, fluorine, CSA, chemical shift anisotropy, spinning sideband. And then when you go to high enough temperature above the gel to liquid crystalline phase transition, you can see a single isotropic peak for the fluorines, indicating that the drug is doing some kind of tetrahedral jumps or reorientations that are highly symmetric so that you don't have any spinning sideband. So that gives you an idea of the drug property. But the interesting thing for us is to really take advantage of the fluorines on this drug to measure distances. And of course, we would want to do that at low temperature where the protein is not moving, the drug is not doing this tumbling tetrahedral jump. And so we go to somewhere around 280 Kelvin. We then measure these spectra as I described earlier for GB1. The readout is the proton-nitrogen 2D correlation spectrum. And you do this, S0S, and you subtract, and you get the map of amide hydrogens that are close to the fluorine. So you see that by doing REDOR, you are basically having spectral edit. You're no longer seeing all the Mi protons, which are a lot. And this protein monomer, the basic molecular weight is 11 kilodalton, it's 110 residues. And you have two copies of these with different chemical shifts. So it gets to be fairly large for solid state. By doing the REDOR dephasing, picking out only the signals of the amide hydrogens that are close to the fluorine, I immediately reduce the number of peaks that I need to resolve. So that's very nice. And the subtraction works really well. The reason is for the detected nucleus, it's identical experiment. The only thing that's changing is on the third channel, the background channel. Of course, we also have 3D experiments separately that allow us to assign the chemical shifts. This looks bad, but in the 3D, you'll see that it's actually very nice. And when I do 3D, I go to a 1.3 millimeter probe, and I'm spinning it up to like this. So I know the underlying chemical shift positions. Then we also do the REDOR in a quantitative way as a function of mixing time. I can follow the intensity dephasing as a function of mixing time to get these quantitative distances. So that's extremely helpful. Let me skip this and basically get to the main point, is that all of these distances help to pinpoint where the tetraphenyl phosphonium is sitting between the two copies of the protein at the dimer interface. And it is known that there are 4 transmembrane helices, but their exact arrangement between the two monomers, the dimer, and displacement between these transmembrane helices, that's the kind of information we want. And by having this drug there sitting in a dimer interface, having hundreds of distances, that basically allows us to get the whole structure. Now, our structure calculation does not attempt to start from nothing. We do take advantage of what's known before, the crystal structure and the MD simulated best guess. And we start from that and we refine against that MD using these hundreds of distances. So we have a docking, and then we allow the protein to wiggle in the MD, always following the distances. So we refined upon the previous structure calculation. This gives you an idea where the 4 fluorines of this drug are sitting relative to key residues in this protein. We always have 2 copies, and we take prior information about what is known about the E14, glutamic acid residue 14, tryptophan 63, and so on and so forth. And now we know where these residues are. So we learn a lot. This binding pocket is actually quite spacious. What stabilizes the complex is some kind of multivalent aromatic interactions between the aromatic substrate and the various aromatic residues of the protein, whether it's tryptophan 63 or tyrosine 60, and so on. So we also learn something about the drug tumbling in this binding pocket at low-ish or moderate temperatures. We can see actually 2D fluorine-fluorine exchange spectrum. So that's pretty interesting. The third example is an amyloid protein, the A beta fibril. And here the idea is to take one of these wonderful fluorinated positron emission tomography tracers. The fluorine 18 PET imaging is very, very common, whether it's for neuroimaging purpose or cancer imaging or whatnot. And you can get these basically off the shelf, getting it from one of the companies. Flutometamol is this aromatic compound that is not really all that different from thioflavine T. All of these aromatic reagents basically have a propensity to bind beta sheet amyloid-rich kind of proteins. And the fluorine is here. Flutometamol is the fluorinated version of a very well-known non-fluorinated A beta imaging agent called a Pittsburgh compound B. It's known as binds A beta fibrils. So we took this and added it to C13 and 15 labeled A beta. And just looking at the fluorine spectrum of the small molecule itself, you learn something about the rigid limit CSA. This is the powder of flutometamol without A beta. Then you bind this to A beta. Of course, everything is a hydrated gel-like sample. And then you can see what is the bound fractions of CSA, how that compares with the dry powder flutometamol. And you can also do quantitative analysis where you can say something about, loosely bound fraction of flutometamol versus tightly bound, because you see 2 signals, slightly different CSA response. By fluorine detection, you learn something about a small molecule property as bound to the protein. But then here, the main experiment that we want to look at is, okay, where exactly does this fluorinated molecule bind? Where is it on the A beta fibril? A beta used is a 40 residue version of the A beta, and we fibrillized it. The chemical shifts look somewhat different from the published chemical shifts, so it's yet another polymorph, but that's not the crucial thing. The crucial thing is we have C13 and 15 labeled peptide, and we have the fluorinated. This is where we decided to develop this new experiment where instead of having the deuterated protein and do this nice proton fluorine experiment, we had to resort to proton fluorine REDOR as detected by carbon-carbon 2. Why do we have to do this? You know, this is complicated. We have these FSLG, proton homonuclear decoupling. The reason is the spectral quality, the line width and so on, is not nearly as good for proton nitrogen to decorrelation for amyloid proteins as you would need. We think it's because these beta sheet amyloid proteins are very densely packed. Every 4.8 angstrom, you have another beta sheet coming and making fibril. So the proton density is very high. It's rock solid. So because of that high proton density, the quality, the spectral quality is not quite high enough to do the direct proton detection. So that's when we turn back to, you know, carbon-carbon correlation, which can be done relatively straightforwardly. So proton fluorine is probed in an indirect manner, and that's why we have the demonstration. Anyway, long story short, it can be done. Shown in blue is the S0 spectrum, where we have all the carbon-carbon particles. And we purposefully are broadening it a lot in order to mimic the kind of broadening we need in order to see the different spectrum. So I have, again, S0, and I have S, and I subtract, and the subtraction gives me the red different spectrum, and that then allows me to say which exact carbon-13 labeled residues are actually close to the fluorinated flutamide. Examples of these residues are shown here. This is in the aromatic region, and there's a phenylalanine 20 as well as phenylalanine 19 in this peptide. There are also valine residues, valine 39 and valine 40, which you can resolve in the aliphatic region of the spectrum. Okay, so you say, all right, that's good. We can say that this flutamidamol, this compound, is bound to two sequential phenylalanine residues. It's also in close proximity to two sequential valine residues at the C terminus. Here, this is the histidine signal along the diagonal. There's another pair of sequential aromatic residues. That's histidine 13 and 14 in A beta. So it's remarkable that this aromatic PET agent go after these sequential same type of residues. And we took these REDOR results and did docking using Haddock, and just to show that, okay, energetically this is reasonable. But the interpretation of these binding pockets is really intriguing because there are not really that many sequential same amino acid right next to each other, HH, FF, VV in this. We think this explains why this flutamidamol compound can recognize A beta regardless of the polymorph. Because A beta has no specific really structure, not only in vitro, that basically every lab makes a slightly different polymorph, but even in vivo, there is polymorphic situation. And so when it's polymorphic, you go, what is the structural feature that this compound will recognize for the A beta? Well, if you have two sequential amino acid residues, then as long as you have a beta sheet backbone, one residue will face one side of the beta strand, the other residue will face the other side. So we think that this allows this drug to recognize one of the two histidines, one of the two phenylalanines, and one of the two valines, regardless of which polymorph you have in the brain. This is the interpretation that we have. And then for saying a little bit more about the translational nature of this ligand along the beta strand axis, you have hundreds to thousands of these beta strands having the same structure. They're hydrogen bonded, 4.8 angstrom for every run of the ladder, you move 4.8 angstrom. So we think that based on the rough dephasing that we get distances in the generally sort of 6 angstrom-ish, let's say between 5 to 7 angstrom. So this fluorine on this drug can sit above one beta strand closest, and then it will be in some distance contact a little bit longer to the adjacent chains. And so the length of this ligand is such that we think it will straddle probably at least 3 beta strands, if not more. We looked at the stoichiometry of the binding closely. It's something like 1 small molecule to 5 A beta. That's overall binding 20% stoichiometry. But out of that 20%, half is relatively tightly bound, this rigid limit CSA, and the other half is a little bit loosely bound. We're trying to explain why, just how saturated is the beta sheet surface by this molecule. So this gives us an idea that you can have a molecule that sits on one beta strand and blocks the next 2 chains. So this is where I want to stop and conclude by saying that homonuclear and heteronuclear distances can be relatively readily measured with existing techniques in solid state NMR, and homonuclear distances are most easily measured by 2D correlation or isotopic spin exchange experiments, spin exchange or active dipolar recoupling. You can follow the class peak intensities to get semi-quantitative distance information. If you have the same isotopic shift but different tensor orientation, then remember CODEX is a really nice technique to measure homonuclear distances and, more importantly, to do spin counting. The heteronuclear distances can be measured using dipolar recoupling. The simplest and most elegant, most robust heteronuclear recoupling technique is really REDOR, because this universal curve feature, and REDOR can be incorporated into various 2-dimensional correlation templates. So it's a very versatile technique. You can insert REDOR into different things. And I should mention that 2D REDOR for carbon nitrogen has been developed by Christian Roniak and Bob Griffin some years ago, and we're here basically taking things in a different way to fluorine. Of course, fluorine spins can allow us to measure distances to much longer range than C13 or N15. So with that, pretty much I want to stop.